In this video, we're going to look at finding the center, interval of convergence, radius of convergence for power series. We're going to let x be a variable, and so the sum from 0 to infinity of a sub n x minus c to the n power is a representative of a power series centered at c. Sometimes you'll only have an x to the n, and if that's the case, then your center is at 0. If you look at the last two lines, the easiest way to find the center is to take the part with x to the n, in this case x minus c, just set that equal to 0, solve for x, and then that'll be where your power series is centered at. Let's look at just identifying the center of a power series. We have the sum from 0 to infinity of -1 to the n times x minus 3 pi all to the 5n power divided by 3n factorial. As far as just locating the center, you look for your x term. You don't have to worry about the exponent, just what's inside. Set that part equal to 0. Solving for x. And so 3 pi is your center. It's just that quick. Now, when you're asked to find the radius of convergence of a power series, then you use ratio test, and that's from a previous homework, and you want to find out what the limit of your ratio is for your a sub n plus 1 over a sub n, absolute value, and we're going to look at that limit and see how x works alongside of it. So for example, we'll jump right into the limit as n goes to infinity. Okay. So this will be the ratio we set up. Just like in the previous homework sections. Okay, so in absolute value, we're going to take our original series, and everywhere there's an n, we're going to use an n plus 1. Okay. Now, dividing by a sub n, basically you just take your original series, take the reciprocal of it, and multiply. Because remember, dividing by a fraction is the same as multiplying by its reciprocal. So I'm just going to copy the original problem upside down. I just run out of room to make a complex fraction, so that's why I'm doing it this way. And close off the absolute value. Okay, so we've got the n plus 1 term divided by the original, but of course I wrote it as times the original flipped. Let's see how this limit works out. We've got the limit as n goes to infinity. Okay. Now from the previous slide, I'm going to recopy. Okay, let's do a little cancellation here. Because these are in absolute values, that -1, whether it's n plus 1 or n by itself, those are not going to matter because it's either 1 or -1, but when you absolute value, it's always a 1. So those just direct cancel. X to the n will cancel that one, but it'll still leave one of those x's up top. Now this limit is only applied to n getting very large. So we can pull out that remaining x. And again, we're doing that because this limit is only applicable to the n variable. Which inside, after all the canceling's done, we have n plus 6 over n plus 7. And what does that limit come out to? That's right, it comes out to 1. For this to converge, that has to be less than 1, which is any number less than 1 unit away from 0 on a number line, because that's the definition of absolute value. So anywhere from -1 to +1 will have a distance or a radius of 1 unit. And that's what you're looking for if your problem just simply asks you to find the radius of convergence. Let's look at one more example. This is also finding the radius of convergence. We're going to bring in a factorial just as a nice reminder of some of the problems we've done in the past. As far as the original setup, still the same thing. We're going to take the absolute value. We're going to do the a n plus 1 over a to the n. Just like the last example, I'm going to do the limit as n goes to infinity. And because I don't have room on this slide to do a complex fraction, I'm going to do the n plus 1 term times the reciprocal of the original. All the n's get replaced with an n plus 1. It's a little tricky right there. 2n plus 1 all factorial times the original, just flip it upside down, dividing by a fraction, same as multiplying by its reciprocal. Okay, so we're going to see where this ratio comes out. And remember, from ratio tests, we want the absolute value of this ratio to come out less than 1. So sometimes they do and sometimes they don't. I'm going to move to the next slide. On the next slide, what I'm going to do is distribute those 2's to the n plus 1. In that first fraction in the absolute value, I'm going to rewrite as x to the 2n plus 2. That'll be the upper left. In the bottom left, it'll be 2n plus 2 factorial. Let's do that. Okay, so that's with the 2 distributed. Remember, it's going to be times the original flipped over. Okay, let's look for some cancellations right off the bat. I see one where the x to the 2n can give us a cancellation. Now, there's still going to be an x squared left over. That's fine. Also, let's remember that factorials you can count down until you get to the part where you need to make a cancellation. That one and that one you can cancel. Okay, now this x squared that still remains in the upper left, I'm going to go ahead and take it out. That's this part. There was still an x squared remaining. Again, the limit is depending on the n, so you can take that x out. What remains now after that 2n factorial cancellation is 1 over 2n plus 2 times 2n plus 1. Well, what's that limit going to be? As the n's get really large, but you have a fixed numerator, that's right, that limit goes to 0. Very good. Now, this time, we have to look at being less than 1, but 0 is always less than 1. No matter what your value of x is, you can put any value of x in here, square it, absolute value, but the moment you multiply by 0, your value is less than 1. Always less than 1. So this one has a radius of infinity. On our first example, our limit come out to 1, and so absolute value had to be within less than 1 in distance from 0 on a number line. But because no matter what x is, you're always going to have a value less than 1. Endless possibilities. You don't have to stay within so many units of 0. Now let's look at interval of convergence. This one is a geometric series. And remember, for geometric series, as long as your ratio is less than 1, it's going to converge. So we actually don't have to put this one through the ratio test like we did the first couple. As long as x minus 6 is less than 1, it's going to be convergent. And again, that's because of geometric series. Remember back from college algebra when you had an absolute value inequality? Absolute value means distance from 0. Let's also remember when we solved compound inequalities. This is the same as keeping x over 6, keeping that within a unit of 0 on a number line. So you can go to -1, but you can also go up to +1. If you multiply through by 6, you get any value of x between negative and +6. At this point, Our interval of convergence is from -6 to +6. But you're also supposed to check the endpoints to see whether or not, if the endpoint is subbed in for x, will that series converge or diverge? If plugging a number into the original problem gives you a convergent series, then you use a bracket. If it does not lead to a convergent series, then you keep it parentheses. On the next slide, we're going to test -6 and +6 to see if either or both of those values result in a convergent series. Okay, so let's look at -6. Subbing that into the original problem, where we had x over 6 to the n is going to be -6 over 6 to the n. Which is -1 to the n. Remember back when we did alternating series test, whatever is next to this sign alternator, which actually there's nothing there, it's like a 1 that you can't see, that's not going to converge. So when x is -6, the result is a divergent alternating series. When x is +6, your series becomes the sum from n equals 0 to infinity. Replacing x with a +6 comes out to just a 1. So the sum from 0 to infinity of 1, no matter what the power is, that's also divergent. Since we have divergence at both endpoints, your interval of convergence is -6 to 6, both with parentheses. There are times when one of the two endpoints lead to a convergent series. So if a number gives you convergence, use a bracket. If not, keep parentheses. Hope this helps.